So let's talk about a geometric interpretation. So what direction is f changing fastest at a point P? So remember, the directional derivative of f in the direction v at the point P is the gradient of f at P dotted with v. And I want to figure out which direction should we move in to make this dot product as large as possible. Now again, one way to make the dot product larger is to just increase the size of v. And that's one of the reasons why we force our vectors v to have unit length. We don't want to be able to play games like that. Anybody give me any thoughts about what direction I should move to make this as large as possible?
The gradient is largest.
Well, the gradient is fixed. So I need a choice for v. So because we're a little bit behind because I had to run to my office because of mechanical issues, let's just speed up a little bit and say this is equal to the length of the gradient of f at P times the length of v times the cosine of the angle. And if you look at this quantity, here's the gradient of f at P, here's v, here's my angle. The length of the gradient of f at P doesn't change as I change v. It is what it is. V has unit length. It is what it is. Only one thing can change. The only thing that can change is the cosine of theta. So which direction should I travel in to make this number as large as possible? Yes?
Perpendicular to v.
Perpendicular to... But we're trying to choose the direction of v. So I want this dot product to be as large as possible.
Exactly coincide.
So I want them to exactly coincide. And so if v is in the same direction as the gradient of f at P, this will be as large as possible. What direction should I go to make it as small as possible?
Perpendicular. Or cosine of 90.
Okay, so if cosine of 90 is not going to make it as small as possible, that's going to make it 0.
Or the opposite.
The opposite. So we want to go in the opposite direction. We want to go negative gradient. So this is the direction of max change. This is the direction of minimum change, or maximum decrease. And then perpendicular is no change. So we now have a geometric interpretation for the gradient. So gradient grad f at P points in the direction of maximum change. And this will be extremely useful when we get to Lagrange multipliers. So imagine you're trying to find the maximum value of a function. Well, we've talked about how to do it. I'm not going to put the life jacket back on. But you're at an interior point, we look and see, are we at a critical point? If we're at a critical point, all the partial derivatives vanish. And then that's a candidate. It doesn't mean that's where we have a maximum or minimum. It means it's a candidate. So let's assume that, sadly, things don't work out. It's not a critical point. Well, if it's not a critical point, we need to move. What direction should we move? How should we try to find the place where the function is largest? Well, the gradient is basically telling you, hey, this is the direction where the function is changing the most, where you are. I'm trying to go to where the function is largest. This is the direction where things are changing the most. Maybe I should move in that direction. Sadly, this is not always the best thing to do. Sometimes this could get you stuck in a local max rather than a global max. And so, for instance, if you go back and imagine something like this. If you start over here, which direction do you want to go? You'd want to go in this direction and you would get to this point over here. and that would be a local maximum, but it would not be the global maximum. You actually want to go in the direction where things are decreasing the most. You know, I'm not a fan of Stalin at all, but one of his good quotes is sometimes you have to take a step backwards to take 2 steps forward. Here, we want to actually go backwards, make our function decrease, so that we don't get trapped in a local max, we can get to the absolute max. That said, if you have no other information, your best bet is, well, I want my function to increase, let me move in the direction of maximum increase. And this is the geometric interpretation of the gradient. Okay, any questions about this? Okay, so this finishes this section on gradients. We have about 17 minutes left. This is Pi Day. So in honor of Pi Day, I thought I would do all of trigonometry in basically a minute. It's going to take a little bit of prereqs to do all this, but it's going to be putting material in the bank for later in the semester. So later in the semester, we're going to get to sequences and series, we're going to get to Taylor series. Let's take some time today and just get this stuff on our radar screen. We will make the calculations far more rigorous later on. But right now, let me just introduce some of the topics and get them, percolating. Right. So it seems a little strange that the way we're going to do trigonometry, which is all about pi and circles, is to use the number e. But it turns out there's a really beautiful connection between the two. So, trig in a day. So the exponential function. One definition is e to the x is the limit as n goes to infinity of 1 plus x over n to the n. This is the compound interest approach. So you get x% compounded n times per unit. 1 unit of time later, this is how much money you would have if you start off with $1. How many of you have seen the compound interest approach? Okay, the other approach is the series expansion. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus yada 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 is the sum, n goes from 0 to infinity, of x to the n over n factorial, where n factorial means n minus 1, 3 times 2 times 1, and we set 0 factorial equal to 1. So both of these definitions we have to be careful. They both involve infinities. This involves a limit with n going to infinity. This involves infinitely many terms. We have to be careful in terms of justifying everything that happens. I will wait till later in the semester, or would be a really good class to take. This is one of the 10% of the times when linear algebra is not the right answer. But still good enough for an A- in the course. What class should you take? Real analysis. So real analysis would justify all of this very rigorously. Right? I will try to give you a fairly good justification. Now n factorial, this is the number of ways to order n people when order matters. So if you think about it, you have n people, you have n choices of who goes in the first box, and then once you have that, you have n minus 1 choices for the second box, all the way down to 2 for the second to last, and 1 for the last. If you think about it, the example people often use is student government. If you talk about counselors, all the counselors are the same. Order doesn't matter. If you're talking about the executive board, the president is different typically than the vice president. Famous vice president once remarked when asking you, what do you do as vice president? He responded, you die, I fly. His job was to go to the funerals and pay respect. It's not quite the same as being the president. Right? Order matters. Whoever's first is different than who's second, is different than who's third. Now the interesting thing is, why do we set 0 factorial equal to 1? Well, 3 factorial is the number of ways to order 3 people, so why should 0 factorial be 1?
There's only one way of ordering 0 people.
Yeah, there's one way of doing nothing. You can't do nothing 2 different ways, then you'd be doing something. It's technically convenient to define 0 factorial to be 1. So if we define 0 factorial to be 1, we have this beautiful formula. So what do you think e to the x times e to the y would be? You would think it's e to the x plus y. But we don't know that. all we know at this point is this is the same as the sum, and it goes from 0 to infinity, x to the n over n factorial. The sum, m goes from 0 to infinity, y to the m over m factorial. If there was any fairness in notation, if this was good notation, then this should equal e to the x plus y. But we don't know that it's equal to e to the x plus y yet. We're going to have to prove that. Okay? What does it even mean to raise something to a number? If I give you x squared, what does x squared mean?
X times x.
X times x, okay. Not a big problem. I won't do x cubed, x to the 4th. X, 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 x. X to the 1/2.
Square root.
What does square root mean? If x to the 1/2 equals y, then we're searching for a number such that y times y equals x. I can interpret fractional powers. I can interpret integer powers. What does it mean to raise something to the square root of 2 power? That is much harder. We'll see later that if I give you more generally x to the r, this is e to the r natural log of x. Or some people like to write ln of x. And we'll see later that that's a great interpretation for what's going on. Okay, so I want to show you now why this rule for e to the x, e to the y is e to the x plus y. So I'm not going to be able to justify everything completely rigorously, but we will be able to get fairly close. Okay, so proof e to the x, e to the y is e to the x plus y. Alright, here we go. E to the x, e to the y is the sum, n goes from 0 to infinity, x to the n over n factorial, the sum, m goes from 0 to infinity, y to the m over m factorial. I have a double sum. I'm going to rearrange the sums. You have to be extremely careful. Some of you have looked at this video that's circulating about the dangers of the sum of the positive integers is negative 1/12. Everything I'm doing can be justified. I'm just going to be a little bit cavalier today. I'm going to group things differently. And I'm going to group things based on how many x's and y's do I have together. So maybe I have x cubed, maybe I have y to the 5th. That would give me a term with 8 variables in it. So I'll take all the terms with 8 variables and collect them together. So this turns out to be the same as the sum. K goes from 0 to infinity. The sum L goes from 0 to infinity. X to the L, y to the k minus L, over L factorial, k minus L factorial. And so I'm just saying, well, let's say k equals 8. I'll take all the terms where the number of x's and the number of y's is 8. So I'll start off with x to the 8, y to the 0, x to the 7th, y to the 1st, and so on and so on and so on. L factorial over k minus L factorial, that looks vaguely familiar. Where have you seen something like that?
Log.
I'm sorry?
Differentiation.
No. I mean, it does occur, not quite there. Pascal's triangle. When we're expanding things in Pascal's triangle, the coefficient would be k choose L. Well, I don't have a k factorial in the numerator, so let's put a k factorial there. So then I have to put 1 in the denominator. I've multiplied by 1, perfectly allowable to multiply by 1. This is now the sum. K goes from 0 to infinity, 1 over k factorial. Now I have a sum, L goes from 0, oh, not 0 to infinity, sorry. L goes up to k. It's technically right if I had written up to infinity because of how we define the factorials of negative numbers. It turns out negative 1 factorial is infinity. So technically I did not write anything wrong, I just wrote something that I did not need to write. So I really should have L only going up to k. Well, k factorial over L factorial, k minus L factorial, that's just our definition of k choose L. So when you do Pascal's triangle, when you expand it out, that's what you get. Alright? We saw Pascal's triangle, we saw that nice fractal picture of it. We'll do some more fractals next Thursday night. X to the L, y to the k minus L. This part over here is just what we get when we expand x plus y to the k. So this is the same as the sum, k goes from 0 to infinity, x plus y to the k over k factorial. But what does that equal? This is just equal to what? Yes.
E to the x plus y?
Excellent. E to the x plus y. My rule is E of input is the sum of input to the n over n factorial. Does it matter if I use the letter n or k? No. And here is a proof that e to the x plus y is e to the x times e to the y. Extremely important fact. Alright. We have just enough time left to do all of trigonometry. Okay? So what I want to do now is, we have our formula for e to the x, and I'm going to just state two nice facts about it. So the first fact is, what is the derivative of a sum? Sum of the derivative. That only works if you have finitely many terms. If you have infinitely many terms, you have to be a little bit more careful. Later in the semester, we will talk about handling issues like this. For now, I will put on my physics hat. I do have a physics degree. I'm allowed to do this. And I'm going to just differentiate term by terms and not really worry. If I take the derivative of e to the x, I get derivative of 1 is
0.
derivative of x. Derivative of x squared.
2x.
It's going to be faster, guys. We're not going to make it. Derivative of x cubed. 3x squared over 3 factorial. 2 over 2 factorial. I cancel the 2. I've got 1 factorial, which is 1. 3 over 3 factorial. I cancel the 3. I get 2 factorial. I get that this is just equal to 1 plus x squared over 2 factorial. The derivative of e to the x is e to the x. Right, you have to justify interchanging the sum and the derivative, but that's a nice start. We call this expansion the Taylor series of x. The Taylor series of e to the x. So we'll do a lot more with Taylor series. So the first is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 dot. What other functions might you want to know their Taylor series for? Sine and cosine. We're supposed to be doing trigonometry today. Turns out cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. And sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 dot. These look a lot like e to the x. And in fact, what's going on is the following. So I is the square root of negative 1. What would I squared equal? Negative 1. I cubed. Negative I. I to the 4th. I to the 5th. I. I to the 6th. Minus 1. I to the 7th. Minus I. I to the 8th. It cycles around. And when you look at what's going on here, if I look at e to the I theta, after you do a lot of algebra, you get cosine theta plus I sine theta. And if you look at the series expansion, every time I have I to an even power, I get a real number. And it'll alternate between plus 1, minus 1. Every time I have I to an odd power, I'll get an imaginary number. And when you group things together, if you plug in formally x equals I theta, you'll get e to the I theta is cosine theta plus I sine theta. Alright, so we have 4 minutes left. That's just enough time to do all of trigonometry. So the key facts that we have is the following. E to the I theta is cosine theta plus I sine theta, and e to the I x, e to the I y is e to the I x plus y. What's the most important relation in trig?
Sine squared plus cosine.
Sine squared plus cosine squared is 1. All right. Pythagoras. E to the I theta times e to the minus I theta. What would that be? That's e to the 0, which is 1. Okay. This is going to be cosine theta plus I sine theta. This is going to be cosine minus theta plus I sine minus theta. The cosine of theta is the same as the cosine of minus theta. The sine of minus theta is minus the sine of theta. So I get cosine of theta plus I sine theta, cosine of theta minus I sine theta. Because these have different signs, the middle terms cancel. And when you expand, you get cosine theta times cosine theta is cosine squared theta. Plus I sine theta minus plus I sine cosine minus I sine cosine, they cancel. I times minus I is 1. Cosine squared plus sine squared. There's our first fact. There's Pythagoras. Cosine squared plus sine squared is 1. The next one we're going to prove is we'll prove the double angle formulas. So you may have seen proofs of the double angle formulas. You know, the standard proof is something along the following lines. Here's angle x, here's angle y. This vertical line is the sine of x plus y. We drop a perpendicular here, we drop a perpendicular here, we drop a perpendicular here. Play lots of games. You can get the formula for the sine of x plus y. I'm going to show you a much faster way to get it. Yes?
Why is cosine of negative theta not negative cosine of theta?
Because if you look at your picture for your circle, if I go up theta like this, or if I go down negative theta like this, they have the same cosine, but their sines are opposite signed. So the cosine of theta is the cosine of minus theta. The sine of minus theta is minus sine theta. Cosine is an even function. Sine is an odd function. So we're going to just quickly end with e to the ix, e to the iy is e to the I x plus y. So this is going to be cosine x plus I sine x, cosine y plus I sine y is e to the I x plus y. Well now, if I expand things, I get cosine cosine, so cosine x, cosine y. I times I is, so the other real term would be minus sine x sine y. Now I have the two imaginary terms, sine x cosine y, and then cosine x sine y. I'm just using FOIL. But this is equal to e to the I x plus y. E to the blah is cosine blah plus I sine blah. All I have to do is now plug in x plus y, and I get cosine of x plus y plus I sine of x plus y. So the only way two complex numbers can be equal, the real parts have to be the same, the imaginary parts have to be the same. Cosine of x plus y, cosine x, cosine y minus sine x sine y. Sine of x plus y, sine x cosine y plus cosine x sine y. You want your double angle formula, you want sine of 2x, take y equals x. You want your half angle identities, you can get every trig formula you need from these two facts. Absolutely amazing how much this does. If you want a really nice challenge, make this picture work. Right? Alright, so this is a good way to end. I thought, in honor of Pi Day, this is a nice way to stop. Now, yes, pi is linked to e. It would be horrible, I guess, not to write down one final formula. Who knows what e to the I pi equals? Yes?
Yeah.
-1. And when you plug in, cosine of pi is -1, sine of pi is 0. This is considered one of the greatest formulas in all of mathematics because it links almost all of our constants.